Hello, and welcome to my first YouTube video. Or, in the event that I upload these in a different order, welcome to a YouTube video. This video is about this thing here. This is a constant current electronic load. It's got active cooling, it's got a big heatsink, and it's got some binding posts over on this side to connect the power supply or battery or what have you under test. Power for the circuit itself goes in here. We'll take a look at the schematic in a moment. The controls are here. Fairly simple. Zoom in a bit. Yeah. Basically, we've got a switch which goes between the low current, this is the low current mode, we can switch it there for the high current mode, and a 10-turn potentiometer to adjust the current that we're drawing. And that's about it. It's fairly simple from a mechanical standpoint. We've got the sense resistors there. Those are 5.5 ohm resistors in parallel. How does it work? Let's take a look. So what is it? What is this thing? What does it do? How does it do it? This is a pretty classic circuit, or at least this part of it is. There's a sense resistor here that the current passes through. There's a MOSFET here with the source to the sense resistor. The ground, circuit ground, is down here. The drain goes to the positive of the device under test, the power supply or the battery under test. And this op-amp here gets feedback from the sense resistor, and we set the amperage we want with this potentiometer up here. These are just pads for the potentiometer, but we'll call it a potentiometer. So we set the amperage we want by setting the voltage at the non-inverting input, and this op-amp tries to keep the voltages here and here the same by turning off and on, and it's going to oscillate. It's going to oscillate fairly quickly, probably around 20 kilohertz if I remember correctly. I really should have left this thing cracked open so I could put the scope on it, but I didn't. The difference between the classic circuit and what I've done here is, instead of using a 1 ohm resistor here, 1 amp divided by 1 ohm equals 1 volt, I've used a 0.1 ohm resistor. So I needed to use the other op-amp in the 358 as an amplifier with a non-inverting amplifier with a gain of 10. So that gets the sense voltage from the sense resistor, amplifies it, and puts it into the driver op-amp that drives the gate of the MOSFET. There's some other stuff on the board as well. The LM7805 here wasn't really necessary, but it's there if I need it. This over here, the other control, other than the potentiometer that I have, is a switch. Single pole double throw switch. The pole of the switch is connected to the top of the potentiometer. And the two throws are connected to VCC and to here. This says 1V out. It's really 1/10 VCC out. So this goes to one throw of the switch, and this VCC out up here goes to the other throw of the switch. If I have 12 volts going in and the switch is switched to the VCC side, I can draw up to 12 amps. But if I switch it to here, if I switch it to the 1/10 VCC switch position, I can't draw as much amps. I can only draw 1/10 of VCC amps, so 1.2 amps if I have 12 volts VCC. But since I have a much smaller voltage over the same potentiometer range, it gives me much finer grained, higher resolution control that I can use. And that's really more useful to me. You might need to accurately select between 10 and 25 milliamps. And that's something that I wouldn't be able to do if the potentiometer was controlling 12 amps across its range. But with the potentiometer controlling 1.2 amps across its range, that's very simple to do. So that's basically what's happening in there. Alright, so if I've already built the thing, what am I doing in this video? Well, originally my intention was to take this to school with me and use the lab equipment there to characterize its accuracy. The problem being, school is shut down, so instead of having access to the Fluke process calibrators and the Fluke 87.5s we have there, what I have are this Mastech 830B and this Unity UT61. UT61 is pretty darn accurate. I have no doubts that I would be able to, pretty closely characterize how accurate this this constant current load was with two of these, or with one of these at an 87.5. We're going to be able to get pretty close though with the Mastech and the Unity. Let's take a look here. Basically, we're going to have to make a choice based on the specifications, which one to use for current and which one to use for voltage. And what it's looking like, what I think I'm going to end up doing, is using the Mastech for voltage, because it's plus or minus 0.5% accuracy versus 1% accurate on all of its current ranges. And I'll use the Unity for current, since its DC current range is 0.5% accurate. Actually, just during the initial setup, I'm discovering a problem I may run into here. This is the input impedance on the Mastech on its DC voltage ranges, which is pretty low impedance. But yeah, we'll run it and see what happens. Okay, this is going to be the power supply under test, my bench power supply. Got it set for 7.4, just like a 2S lithium ion battery, because that's, sort of a common thing I might try to test with this. Let's see how it goes. Okay, so I'm starting on the low current range. So let's start winding it up. The Mastech down below is on milliamps. The Unity clearly is on amps up above. Let me see if I can adjust the Mastech, get rid of that shadow. Not really. I can still kind of see it. So this is looking pretty good so far. That's looking real good. Start plugging things into a spreadsheet. Oh, we hit current limit on the, yeah, hang on. Go ahead and turn that all the way up. That's really not so bad at all. A little bit of wiggling. I'm not sure what the wiggling is, if it has to do with components heating up or just the pot settling down a little bit once I stop touching it. So yeah, on this low current range, I actually have really too much control once I get up in this range. And there we are maxed out, which is about what I would expect for 1/10 VCC, I know it's reading 12.6 there, but it's probably closer to 13. Yeah, it's not too bad. Okay, sorry for the angle here. The camera's a little bit shorter than I am. But we've got the spreadsheet set up to convert the millivolts. We're doing times 10 and then dividing by 1000. That's going to give us a number that's going to be, you know, roughly equivalent to the amps we should be getting. Amps, millivolts we're just putting in. And this is going to be the standard percent error equation. We're using amps as the true value and millivolts as the millivolts converted as the measured value. So these are just dummy values just for testing, but you can see with 105 millivolts we get 1.05 millivolts converted compared to 1 amp, gives us 5% error. Maybe one more. I've gone ahead and wound the voltage down so we can really crank the amperage and see what this thing can do. Here we go. I want to avoid going much beyond 30 watts, so if we get near 10 amps, I'm going to cut it there. Actually, for that matter, I don't really want to go above 10 amps because I'll blow the fuse in my meter. Right. Yeah, we're going to hit current limit on my 5 amp max power supply. That seems reasonable though. Can max out the power supply, that's good enough test for me. Okay, so I've got the results here. They're pretty not bad. There's a couple of outliers. Not really sure what happened with this minus 0.96 here. That's a weird one. The 25% error doesn't really bother me too much. It's right at the bottom of the range, so I would expect some error down there. And really, it's just because the numbers are so small. The absolute error that we've got here is only 1 milliamp. Just the fact that there's only 5 milliamps to play with, so 1 milliamp error there is pretty large percentage-wise. But otherwise, these numbers are great. Got an average error of minus 0.39%. So yeah, that's gonna be really good for testing batteries. I'll be able to use just a voltmeter across the sense resistor to tell what kind of amperage I'm drawing out of the batteries. That's pretty good. Okay, so I mentioned earlier the relatively low input impedance on the Mastech could have screwed things up, and certainly the readings look okay, but I wanted to just see how much they could have screwed things up or did screw things up. So 2 parallel resistors. We're going to treat the Mastech just like a resistor. We'll do product over sum. We've got 1, 6 zeros, 1, 2, 3, 4, 5, 6. Rounding up by about an ohm there, at least according to the reading from the Unity. And then 1, 2, 3, 4, 5, 6. For the input impedance of the Mastech, plus the 0.1 ohms for the sense resistor. Bring the calculator in. Is that going to be visible or in focus? Now it is, kind of. Yeah. Got 1, 2, 3, 4, 5, 6 times 1. 5, 6. Let's try that again with me not being an idiot. 1, 2, 3, 4, 5, 6 times 1 divided by, come on, parentheses. Parentheses key on this calculator is not good. 1, 2, 3, 4, 5, 6. Right? Plus. That's better. That's what we'd expect. So, it's really not bad. So, yeah, that's about that. It works. It's accurate enough for my needs. It can handle relatively high amperages and wattages, or at least as high as I need it to. Yeah, good project, working project.